In the last video, we talked about the antiderivative version of two of our many different derivative rules. We talked about the antiderivative version of the power rule, and we talked about the antiderivative version of the coefficient rule. In this video, what I aim to do is talk about the antiderivative version of all the other rules. Well, kind of. I mean, some of them we can kind of ignore. The first of the rules we'll spend about, 10 seconds on. The fact that the derivative of x equals 1 tells us that the antiderivative of 1 is equal to x, or technically x plus c. Just like technically the fact that the derivative of x equals 1 is a rule, but it's not something you worried about a whole lot. You learned it really quickly and it didn't even feel like a rule once you learned how to take derivatives. The antiderivative of 1 is equal to x is technically a rule, but trust me, it's not going to bother you too much. The fact that a derivative of a constant equals 0 was another one of those kind of simple rules when we're taking derivatives that you didn't worry about a whole lot. And the good news is for antiderivatives, we don't have to worry about it at all. It really just justifies why we tack on a plus c. If the derivative of a constant equals 0, then the antiderivative of 0 equals a constant. And anytime we're taking an antiderivative, we can always think about there being a plus 0 there. And that'll end up being why we need to add a plus c to our answers. It's not a rule I should leave out altogether, but it's definitely not one where we have to spend much time. Next rule I want to talk about in this video is probably the nicest one of the entire video. The fact that the derivative of e to the x is just equal to e to the x means that the antiderivative of this e to the x is just going to be equal to this e to the x. Although technically I should tack on a plus c. Just like you love seeing e to the x when we're taking derivatives, you're going to love seeing e to the x when we take antiderivatives. And when we were taking derivative exponentials, the base was almost always an e because things work out so nicely, but technically it doesn't have to be an e. I could ask you to take the derivative of, 2 to the x. And if I asked you to take the derivative of 2 to the x, if you remember stuff really well, you'd say it's not just 2 to the x, it's almost 2 to the x. I have to multiply that by the natural log of 2. Well, if the derivative of 2 to the x is equal to 2 to the x times the natural log of 2, then what would the antiderivative of 2 to the x be equal to? Well, it's almost just 2 to the x, but the derivative of 2 to the x does not produce 2 to the x. It produces 2 to the x times the natural log of 2. I'm going to have an extra natural log of 2 over on this side. How do I get rid of that extra natural log of 2? Well, let's divide by the natural log of 2. When you're taking derivatives of exponentials, you have to multiply by the natural log of the base. When you're taking antiderivatives of exponentials, you have to remember to divide by the natural log of the base. And if you have a hard time remembering, just take the derivative of the right-hand side and make sure that you recapture this b to the x. And yes, just so somebody doesn't point it out, I should tack on a plus c right here. If you haven't already gathered this, tacking on these plus c's is a little bit tedious and something you're often going to forget to do. And it's not a big deal, but I guess so that it's not a do as I say and not as I do, I should tack on the plus c. That's it with exponentials. What about logarithms? Okay, this one's pretty interesting. More often than not, when we're taking derivatives of logs, the log that we were taking the derivative of had a base of e. We saw the derivative of natural log of x way more than we saw the derivative of log base 2 of x, for example. But we're able to take the derivative of either one. Let me start with the more common example. The derivative of the natural log of x equals 1 over x. Therefore, the antiderivative of 1 over x should be equal to the natural log of x, I guess plus a c. And that's true, although there's a couple things to be careful of here. In this statement over here with derivatives, x is assumed to be a positive number because the log of a negative number is not even defined. So when I ask you for the derivative of the natural log of x, implied in there is that x, the variable, is positive. Because if x were negative, this wouldn't make any sense at all. But over here, that's not the case. When I ask you for the antiderivative of 1 over x, x can be any number you want except for 0. 1 divided by negative 5 is perfectly well defined. So I have to be a little bit careful. For this statement to make sense, since the implied domain of the question includes both positive and negative numbers, I can't just leave the answer the natural log of x. Because think about if I'm letting x represent negative 5, then over here in my answer I'd have the natural log of negative 5. But the natural log of negative 5 is not defined. You can't take the log of negative numbers. To get around that, all we have to do is tack on an absolute value symbol here. The derivative of natural log of x equals 1 over x. You don't need any absolute value symbols because implied is that we're only letting our variable x be a positive number. But the antiderivative of 1 over x is not just the natural log of x, it's the natural log of the absolute value of x, because implied in the question is x can be positive or negative, just not 0. Another comment here. This is really tricky, the fact that the antiderivative of 1 over x is equal to the natural log of the absolute value of x. Because what you'd probably think to do here, if you saw this question, is be like, oh, 1 over x, that's the same as x to the negative 1 power, right? And I'd be like, yeah. Then you'd be like, all right, so I'm just going to use the power rule. The power rule for antiderivatives tells me that I have to add 1 to this exponent. So instead of being negative 1, it's going to be negative 1 plus 1, which is 0, I guess. And then I'm going to make sure that I divide by 1 more than that exponent. So negative 1 plus 1, which would be 0, I guess. It's really tempting to try to use the power rule when you're asked this question, what is the antiderivative of 1 over x? But it doesn't work. You can't use the power rule to figure out the antiderivative of x to the negative 1 power because you end up dividing by 0, so you get something that's undefined. In fact, when we talk about the power rule for antiderivatives, what I wrote up here, I kind of lied to you by omission. I shouldn't have said that the antiderivative of x to the n dx is 1 over n plus 1 times x to the n plus 1 plus c. What I should have said is that rule holds as long as n does not equal negative 1. That's not a caveat that we needed with derivatives, because with derivatives we didn't end up doing any division, so we didn't have to worry about dividing by 0. But that is a caveat that we need with antiderivatives because of the fact that we introduced division. I debated putting this in the last video when I taught you this, but I thought that might just confuse things and I should wait till I teach you this natural log rule before I show you that technically you can't use the power rule in this case. So what I'm saying is just remember, when you see 1 over x, don't change it to x to the negative 1 power and try to use the power rule. The power rule is not applicable in this case. The antiderivative of 1 over x dx is the natural log of the absolute value of x plus c. And you might be like, right, that works for natural log, but what about the fact that the derivative of log base 2 of x, for example, is not just 1 over x, it's 1 over x times the natural log of 2. Doesn't this create another different antiderivative rule? And the answer is no. I mean, you could create another new antiderivative rule if you wanted, but you don't need to. What you could do instead, if somebody asked you to take the antiderivative of 1 divided by x times the natural log of 2, is to just think that 1 over the natural log of 2 is a constant. So really what they're asking you is the antiderivative of 1 over the natural log of 2 times 1 over x. And since this is a constant, it serves as a coefficient. I can pull it out in front of my antiderivative symbol and just take the antiderivative of the 1 over x part. To take the antiderivative of the 1 over x part, I can use this rule that I already have, and I get 1 divided by the natural log of 2 times the natural log of the absolute value of x plus c. The antiderivative of 1 over x times the natural log of 2 is equal to 1 over the natural log of 2 times the natural log of the absolute value of x plus c. And you're like, wait a minute, that doesn't seem right. If the derivative of log base 2 of x is 1 over x times the natural log of 2, shouldn't the antiderivative of 1 over x times the natural log of 2 be equal to the log base 2 of x plus c? And actually it is. It's just not simplified. You probably don't remember these log simplifications, and that's totally fine. But I could rewrite this as the natural log of the absolute value of x divided by the natural log of 2. And then if you happen to remember the change of base formula, and I know you don't, and that's okay, you could rewrite this expression as the log base 2 of the absolute value of x plus c. The point that I'm trying to make is this expression is equal to this expression using some complicated pre-calculus algebraic simplification that frankly I'm not too concerned with. The fact that the derivative of the log base b of x is equal to 1 over x times the natural log of b, and therefore the antiderivative of 1 over x times the natural log of b is equal to the log base b of x is not a special rule that we need. We can use this 1 over x rule and our coefficient rule to come to the exact same conclusion. Maybe an unsimplified version of the exact same conclusion, but I'm not worried about it. I got to pick my battles. That brings us to trig, which is hard from a teaching perspective. There's a limited amount I can do with trig in a calculus class because there's a limited amount of trig that students remember when they step into a calculus class. We've gone through these 6 different trig derivative rules in our class, but really we've kind of focused on the fact that the derivative of sine is cosine and the derivative of cosine is negative sine. Those were the 2 that were by far the most important. I personally also memorized that the derivative of tangent is secant squared, and the derivative of secant is secant times tangent, and that allows me to kind of recall that the derivative of cotangent is negative cosecant squared, and the derivative of cosecant is negative cosecant times cotangent. But asking a student to memorize all those facts is a bit much. I mean, really, if you leave this class just remembering that all 6 trig functions have derivatives, and maybe these 2 you have memorized, and the other 4 you Google when you need them, I think you're doing just fine. Well, when we talk about antiderivatives, it's going to be kind of the same. The fact that the derivative of sine equals cosine tells us that the antiderivative of cosine must be equal to sine, technically sine of x plus c. And that's a rule I would very much like you to have memorized. And similarly, because the derivative of cosine equals negative sine, the antiderivative of negative sine must be equal to cosine. But rather than tell you the antiderivative of negative sine, I'm going to tell you the antiderivative of sine. Because if we were asked the antiderivative of negative sine, we could just take the negative and bring it out in front of the antiderivative symbol. You might be thinking cosine of x plus c, but that won't work. Because if you take the derivative of the right side of the equation here, the derivative of c goes away, the derivative of cosine produces negative sine. But we don't want to produce negative sine, we want to produce positive sine, so we better have a negative written right here. The fact that the derivative of cosine equals negative sine means that the antiderivative of sine equals negative cosine. And if you remember that the derivative of sine had something to do with cosine, the derivative of cosine had something to do with sine, and one or the other was negative, but you couldn't really always remember which one was which, and sometimes you got it right and sometimes you got it wrong, well, bad news, right? Now it's going to be even harder. The derivative of sine makes a positive cosine, but the derivative of cosine makes a negative sine. The antiderivative of cosine makes a positive sine, and the antiderivative of sine makes a negative cosine. That might be a little bit challenging to remember, but remember you can always check your answers. Take the derivative of negative cosine and make sure you get positive sine as your answer. If so, you're feeling good about this statement. If you have those 2 rules, you're in pretty good shape, but I'd be lying to you if I said that the other 4 were never important. My advice for the other 4 is kind of look at these answers, secant squared, secant times tangent, and cosecant times cotangent, and just kind of sort of remember those. And if you're ever in the case where somebody asks you to take, I don't know, the antiderivative of 4 cosecant squared x, for example, what you do is first take the 4 and move it out in front using our coefficient rule. And then maybe be like, wait a minute, cosecant squared, that seems vaguely familiar. Was that ever the answer to a derivative question? I think it was. Maybe at that point you have to Google, or maybe if you're really good, you'd be like, the derivative of cotangent was almost cosecant. It was negative cosecant squared. So therefore, the antiderivative of cosecant squared is going to be almost cotangent. It's just going to be negative cotangent. So I get 4 times the negative of cotangent of x plus c. In other words, negative 4 cotangent x. I guess what I'm saying is if you feel overwhelmed with memorization, you don't need to come up with antiderivative equivalents for these 4 rules. But in case you want them handy, let me write them over here. The antiderivative of secant squared x is equal to tangent of x plus c. The antiderivative of cosecant squared is equal to negative cotangent of x. The antiderivative of secant times tangent is equal to secant of x. And finally, the antiderivative of cosecant times cotangent is equal to negative cosecant of x. And technically, for all 4 of those, we should tack on a plus c. Definitely understand the 2 blue ones. These bottom 4 ones are, I don't know, optional-ish. I'll sort of leave that up to you. Moving right along, what about inverse trig? Well, as we get further and further into our derivative rules and start to deal with functions that appear less and less commonly, I'm going to care less and less about our antiderivative rules. But it turns out that 2 of these rules will be really useful when you learn some advanced techniques of antidifferentiation in a Calculus 2 class. So it's way beyond where we are right now. But eventually, the fact that the antiderivative of 1 over 1 plus x squared is equal to the arctangent of x, and the fact that the antiderivative of 1 divided by the square root of 1 minus x squared is equal to arcsine of x will be really useful. These other 4, definitely less important, if important at all. But I think these first 2 are rules that'll benefit you to know. The fact that the antiderivative of 1 over the square root of 1 minus x squared is equal to arcsine of x is very useful. So maybe add that to your list of memorization. Similarly, the fact that the antiderivative of 1 over 1 plus x squared is equal to arctangent of x will be something that you definitely need to know for a Calculus 2 class. But the rest of these you can basically ignore. Arcsecant and arccosecant are just so obscure that they hardly ever show up, so it's really not that important. And arccosine and arccotangent we don't need, because look at what would happen if somebody asked you to take the antiderivative of -1 over the square root of 1 minus x squared. What you could do is say, well, I can treat that -1 as a coefficient and pull that out in front of my antiderivative symbol and make it the negative of the antiderivative of 1 over the square root of 1 minus x squared. But the antiderivative of 1 divided by the square root of 1 minus x squared is something I already know. That's arcsine of x. Therefore, the antiderivative of the negative of 1 over the square root of 1 minus x squared is just equal to negative arcsine of x plus c. We don't need a rule corresponding with this derivative because we can just factor the negative in front of our antiderivative symbol and use this rule instead. Wait, that's kind of a strange result. Does that mean that negative arcsine of x is the exact same as arccosine of x? No, not quite, but negative arcsine of x plus an arbitrary constant is the exact same as arccosine of x plus an arbitrary constant. It just works for different constants. What? That's way beyond the scope of our class. Maybe I shouldn't have even said any of that. The point is you don't have to worry about another antiderivative rule for 2 here, and by the same logic, you don't have to worry about an antiderivative rule for 4 here, because if you pull the negative out in front, what you're left with, you could take the antiderivative of using this arctangent rule. One last major rule that we care about, and the good news is you probably already assume that it's true. When I take the derivative of the sum of 2 different functions, I can just take the derivative of each of the functions individually. Wouldn't it be great if, when I'm being asked to take the antiderivative of the sum of 2 functions, I could just take the antiderivative of each of the functions individually? Well, I like it when I can give you good news, and the good news here is absolutely you can. If I ask you to take the antiderivative of, I don't know, x squared plus 4x plus 1, what you can do is take the antiderivative of x squared, which if you're really good with the power rule, you might be like, well, the new exponent needs to be a 3, but the antiderivative of x squared isn't just x cubed because the derivative of x cubed would give me 3x squared, not x squared, so I need a 1/3 out in front, and then add to that the antiderivative of 4x. Let's see, how's that work? The 4 is just a coefficient, so I can bring that out in front. And then I need to know what's the antiderivative of x. What do I take the derivative of and get x as my answer? Well, I'd have to start out with an x squared, right? Because when I'm using the power rule, I'd subtract 1 from the exponent. Right, but you'd bring that 2 down in front. The derivative of x squared is not x, it's 2x. So I need a 1/2 out in front here to cancel out the 2 that I'd bring down using the power rule if I wanted to recapture the x in this 4x. What about the derivative of 1? Well, that's just equal to x. If I took the derivative of 1/3 x cubed plus 4 times 1/2 x squared plus x, which by the way I could clean up and make 1/3 x cubed plus 2x squared plus x, what I would get is this is my answer. What that means is this is an antiderivative, but remember this symbol is not asking me for an antiderivative, it's asking me for the antiderivative, so I should tack on a plus c here and here. If you're really nitpicky, you should be like, wait a minute, shouldn't this be 1/3 x cubed plus c plus 4 times 1/2 x squared plus c plus x plus c? Shouldn't there be 3 different c's? And yeah, there should. Because what I'm doing here is I'm taking the antiderivative of f of x and getting capital F of x, which itself has a plus c in there, and the antiderivative of g of x to get capital G of x, which also has a plus c in there. But good news, I don't have to write all those plus c's because the sum of all those arbitrary constants is itself just a constant. So I can just write plus c once at the end and be good with things. You might notice that we're almost to the end of this video and you might be like, how is that possible? We haven't gotten to any of these really complicated derivative rules. I mean, the hardest part of taking derivatives is properly using the product rule, the quotient rule, and the chain rule, right? This was the majority of this journey of taking the derivative of functions. Are there antiderivative versions of the product rule, the quotient rule, and the chain rule? And the short answer is yes, there are, but not for our class. This will be, loosely speaking, the major challenge of Calc 2. Learning how to undo the chain rule, loosely speaking, or undo the quotient rule and the product rule. And it's not straightforward. It's really challenging. This one ends up involving something called U substitutions, and these end up involving something called integration by parts. And it's a big mess, and we'll spend a lot of time on that in a Calc 2 class. But in this video, we're just trying to get an intro to antiderivatives. So this is way beyond the scope of this section. So it's not the type of questions that you're ever going to see. Those are all the rules that we have for antiderivatives. I know that's overwhelming. You might think there's no way you're going to be able to learn all those, but I think you'll see that it's more manageable than you think. Because of the background that you have with derivatives, this stuff won't be that bad. And to prove that to you, in the next couple of videos, I'm just going to do examples. And hopefully what you'll see when you see these examples is eventually you'll get to the point where you're like, yeah, I could have done that on my own. And then, well, you'll be able to do it on your own.